Okay, we can start now with the next lecture. Our teacher is Professor Hans-Martin Fied from the Free University of Berlin. And also during the last few years, he has spent a lot of time in Novosibirsk at the International Tomography Center because he was a PI of a grant from the Russian Science Foundation. Hans-Martin got his PhD in Heidelberg, I guess with Professor Hauser, and then he worked at the Free University of Berlin for many years, and also as a visiting scientist, he worked quite a lot at IBM, which was actually famous for its NMR group in the old days. And also he spent some time at the Weizmann Institute of Science, and he's also a frequent guest in Novosibirsk. Hans-Martin will tell us about light-induced nuclear spin hyperpolarization. As usual, we have all questions at the end of the talk. So to ask a question, please write in the chat box. You can write actually in advance during the lecture, but all questions will be answered after the lecture. Alternatively, you can also raise your hand by pressing the corresponding button. So please, Hans-Martin.
Thank you, Kostya, for the introduction. I hope that there will be no technical problems during the next 60 minutes because my internet connection is rather weak, and I don't know whether it will last for more than 60 minutes. So I'm going to talk about light-induced nuclear spin polarization, and we'll first give a short outline. We will start with a reminder what polarization is, what dynamic polarization or hyperpolarization is, and then why we care for the polarization. I will talk about particularly about the nature of light-induced DNP, then about the mechanisms of light-induced nuclear polarization in solid phase and in liquid phase. We'll continue with some experimental approaches, and later I will talk about ways to characterize short-lived radicals and their reactions. And if time allows me, I'll end with some applications. So first, when we talk about hyperpolarization, there's necessary to start with remarks on the sensitivity of nuclear magnetic resonance. We all know that it is a very powerful spectroscopic method, and that during the last 7-8 decades, it has been used for many investigations in all kinds of science, in physics, chemistry, medicine, material research, and so on. But even with all the new techniques and methods, NMR still has one problem, or three problems, as I was told. First problem is low sensitivity. Second problem is low sensitivity. And the third problem is low sensitivity. And the reason is a small interaction of the nuclear spins with the magnetic field. It is of the order of 10⁹ Hertz, whereas we have in optics interaction which is 5 orders of magnitude at least bigger, with 10⁻⁴ Hertz. So in optics we can see a single quantum. So in nuclear magnetic resonance we need for a decent signal to noise more than 10 to the 5 spins that act together. However, what we have is a negative interference of oppositely oriented spins. That's why the signal intensity is proportional to the spin order, whether all spins are aligned or whether they're randomly oriented. In thermal equilibrium, we have a polarization which is only 10 to the minus 4 of full polarization at standard magnetic field and temperature. And one solution to increase the sensitivity of NMR is producing non-thermal spin polarization. And that's what I'm going to talk about. So coming back to spin polarization and to hyperpolarization, the polarization is the normalized population difference of the states involved in the NMR. For spin 1/2 with 2-level systems, it is just the normalized population difference. For more complicated systems, the name polarization is used for a description of spin order, and it has to be given by several numbers. At ambient conditions, as I mentioned before, it is tiny, the polarization. For protons, it's only about 10 to the minus 4. But we can make efforts to get away from the thermal equilibrium and create what's called hyperpolarization. This term is often used equivalent with dynamic nuclear polarization, DNP. It's a little problem that DNP is often used for only a special subset of hyperpolarization techniques. So we always have to say what we mean with DNP. So hyperpolarization is in most cases used for any type of non-Boltzmann polarization, non-thermal polarization, even if it's smaller than the Boltzmann polarization. As you probably know, hyperpolarization is often characterized by what's called a signal enhancement factor, usually termed epsilon. To say what gain in NMR sensitivity we got. But this term I will rarely use in my talk because it is usually badly defined. You always have to say where, under what conditions the normal NMR signal is taken, whether at high field, at low field, at cryo temperatures, at ambient temperature, and so on. Hyperpolarization, by the way, is not limited to nuclear magnetic resonance, but it's also used for mainly for signal enhancement in electron magnetic resonance. The example is what's called CID-EP, chemically induced dynamic electron polarization. So examples of nuclear hyperpolarization are standard Overhauser DNP or DNP with solid effect based on thermal mixing or on the cross effect. There are other examples, light-induced dynamic nuclear polarization, polarization by optical pumping, hyperpolarization by exploiting parahydrogen, or in the old days, mainly used Hartmann-Hahn cross-polarization in heteronuclear solid-state NMR, or also some hyperpolarization is obtained by the nuclear Overhauser effect, which many of you may know, or by selective relaxation. With all these techniques, you create non-thermal polarization. Here we will focus on light-induced DNP, and there are several subgroups of these techniques: optical nuclear polarization, also sometimes called triplet DNP, in the solid phase. In the liquid phase, it's CIDMP, or when we use in addition irradiation in the microwave or in the radio frequency range, we talk about microwave-induced ONP or SNP. Here, I will start with light-induced nuclear spin polarization in solid matrix. As I said, it's termed usually optical nuclear polarization, ONP, or sometimes now triplet DNP. And I will start with an example of pantacene, molecule shown on the right-hand side. Here, what you do, you have 4 steps of creating your polarization. You start with creating high spin order in a primary system, spin system. Here, it's the polarization of the electronic triplet systems. Then you have a transfer step where you couple, your electronic triplets with nuclear spins. And by certain techniques, which we will discuss a little later, we can transfer partly our electron spin polarization to nuclear spins in the neighborhood of the electronic spins. And now the local nuclei are partly polarized. And then we can transfer this polarization, we can distribute in our solid matrix by spin diffusion. That's how we polarize a full crystalline matrix, for example. Here, we have to talk about how this coupling is between the electronic and the nuclear spins is done. That's for the liquid and for the solid phase rather similar. You can use either the stochastic parts of your Hamiltonian, giving rise to a fluctuating interaction between the 2 spin reservoirs. So by 0 quantum or double quantum relaxation processes, as shown in the upper picture, we can couple the different levels that are involved, or in the lower part of the picture, and the B is shown how we can use coherent polarization by a stationary interaction. And we can do it by matching fields experienced by the electron spins and the nuclear spins. For example, we can match the precession frequency of the nuclear spins with the spin motion of the electron spins around the microwave or radio frequency field B1. So the nutation frequency of the electrons is matched with the precession frequency of the nuclei. And this matching is can be equivalently being described by so-called level anti-crossings. And that's here shown in an example. We have optical nuclear polarization in an anthracene crystals, which is doped with phenazine. Phenazine is shown in the shown here in the little reaction on the upper right corner, and it's doped into in the middle also, and it's doped into anthracene as shown on the bottom of that. And now, once you go to the picture on the right-hand side, you see a field dependence of the polarization, which is shown here in arbitrary units. And what you see is a superposition of two features: a wide curve going up to 400 millitesla, a broad one, which is given by the Overhauser effect of the excitons of the present in the anthracene matrix. That's the Overhauser, the fluctuating interaction. And on top of that, we see a narrow feature shown by the right arrow, which comes from a level anti-crossing of the radical pair, which is formed between the protons of the anthracene and the phenazine. A proton of the anthracene is transferred after light absorption to the anthracene. And this radical pair has a spin Hamiltonian where we have a level anti-crossing. And this is shown here in this slide. When we vary the Hamiltonian using an external parameter, here in our case, mainly the external magnetic field, the sum of the levels, or maybe all of the levels, vary with the magnetic field. And there are cases when two levels cross each other. That's shown on the left-hand side. It's called LC, level crossing. And when we have some coupling of some interaction between levels, between spins, this level crossing changes into what's called avoided level crossing. The levels do not cross each other as in the left-hand case, but near the crossing point, they repel each other. and the distance is usually the related to the interaction element. The minimal splitting between the levels is 2 times the coupling element. And here in this case, when we have this coupling, the eigenstates in that region of the level anti-crossing are no longer the pure cases of the spin states, but they are combinations. We have a mixture of, for example, phi 2 to phi 1. And we have as eigenstates these linear combinations. And this mixing of states changes the basic properties of the whole Zeeman system, and we get what's called polarization transfer. I'll come to that later in more detail. Here we see such a more complicated case in the solids matrix of the phenazine-anthracene system. And we see in the middle the level crossings which occur when we have the zero field splitting tensor and superimposed the Zeeman variation of the Zeeman energy, which starts growing linearly with the magnetic field. And at the two blue circles, we have these level crossings. And we look in more detail, which is in the upper figures, we see that because of hyperfine splitting, this level crossing is seen as two level anti-crossings. The level anti-crossings between the red and the blue and between the magenta and the black eigenstates. So, because of these two level crossing in the left case, where we have orientation along the x-axis of the molecular zero field splitting tensor, we get a superposition of two mixed pairs of levels, one giving you a broad Lorentzian looking curve and another narrow Lorentzian, which is shifted because the two level anti-crossing are a little shifted. I'll come to that later. And we get this funny superposition of two oppositely phase Lorentzian curves. The same is shown for the orientation of the crystal, so that the zero field splitting tensor is oriented parallel with its z-axis along the external magnetic field. So for getting the maximum polarization of the nuclear spins, we have to tune the magnetic field to the level crossing region. That means in such a crystalline system, we have to align the system along the magnetic field with one of its axes of the zero field splitting tensor, the X or the Z case, and then to go with the magnetic field to the level crossing region. If we misalign the zero field splitting tensor with respect to the magnetic field, then the level crossing will get broader and less pronounced, because the minimum splitting between the level becomes much bigger, and then the admixture is getting weaker. So, as I told you, we had the system with a radical pair, where after the light irradiation, one of the hydrogens of the anthracene is transferred to the phenazine. This is a short-lived intermediate radical pair which goes back once the light excitation is over. So similar radical pair systems will show up in many cases of light-induced nuclear spin polarization. And here I show 4 different cases. In the rigid systems, it can be either done between 2 non-covalently bonded parts in the 2 molecules in the solid matrix, as it was done in the phenazine-anthracene system, which is shown on the right-hand side. Or it can be in 1 molecule. You can create 2 sets, 2 radicals. So we get a biradical in the solid state. Or that's shown on the left-hand side, that's symbolized there. Or we can have in mobile system, in liquid spin systems, we can also have 2 radicals on 1 molecule, biradicals, or we can have, that's the left side, or we can have it in 2 non-covalently bonded molecules that are called radical pairs, R and P. So let's go to the liquid phase. And there, light-induced...
Hans-Martin, I'm sorry, I see that there are 2 questions in the chat which are related to ONP. Maybe you can answer to these questions before you get into details of CRENP.
Okay.
Would it be okay?
Yeah.
Okay, so Syed Siptai Razi is asking, why are you choosing pentacene? What are the criteria to design the molecule to show the triplet DNP?
Okay. First, it should have a selective population via the excited singlet state, then going to the electronic triplet state. What you need is a big polarization of the electronic spin system, and this is done by spin selective inter-system crossing from the directly excited singlet state. And this selective inter-system crossing is due to the geometry of the molecule, when it's biggest, it's flat molecules where you have different intersystem crossing along the in-plane direction and the normal to the plane direction. So what you use is this planar molecules, and then you have a high electronic spin polarization. Of course, doped crystals, in doped crystals, what you need is similar size and geometry of the guest molecule and the host matrix molecule, that the guest molecule can fit in a well-defined geometry. So these are the criteria which were used in this case of anthracene plus phenazine. So very well known matrix, for example, is fluorine, also flat molecule. This you can dope with acridine or also phenazine or with anthracene. And in many of these cases, you have these short-lived radicals that are formed between host and guest molecules. Is this enough for this question?
Yes, yes, he says yes, yeah. Also, one more question from George Menseljan. I'm a bit lost. Is it a zero field splitting or hyperfine coupling tensor that enables the legs in ONP with pentacene?
In the, okay, the zero field splitting tensor is mainly for this selective polarization of the electronic spins. It's a mixture of zero field splitting tensor and Zeeman interaction of the electronic of the molecules, and the coupling of the electrons to the nuclei on the same molecule is given by hyperfine interaction. And in the solid, you have the full hyperfine tensor, whereas in the liquid, you have only the averaged hyperfine coupling tensor. And when you have the full hyperfine tensor with all the terms of the anisotropy of the hyperfine coupling, you have these four level anti-crossings. When you have only the averaged scalar hyperfine interaction, then you get only two of these level crossings, and I come to that point later when we discuss in more detail the liquid state hyperpolarization. Yeah, so what you need for the polarization transfer from the electronic spins to the nuclear spins is hyperfine coupling. That's clear? If yes?
Well, I don't. Okay, thank you for the answer. And so the zero field splitting originates from the fact that we have a triplet state. So spin is greater than 1/2 coupled to multiple electrons.
So yeah, it is a spin exchange interaction, but because of the non-spherical shape of the molecule, it is different in different molecular parts. So you can go to a coordinate system and find the principal axes of this of this zero field splitting tensor. That's how it is done, how it is analyzed and described in optical studies, but also in the studies of hyperpolarization.
Okay, very clear, thanks. So, Hans-Martin, sorry for interrupting you.
No, that's fine.
We can now move
on
to
Kingdom. You don't steal my time for the presentation.
We don't, for sure.
Okay. So, we come to the liquid state, and the name of the technique in liquid state is chemically induced dynamic nuclear polarization. It's a kind of historical name because it was used in analogy to the Overhauser DMP in principle. Again, also same as in the solid state, we have light-induced electronic triplet states. And we have hyperfine interaction that leads to the coupling with the nuclear spins. So the chemically induced dynamic nuclear polarization relies on what's called the principle of spin conservation, meaning that all chemical reaction between, for example, of forming a short-lived intermediate radical system, they're all spin selective. All chemical reactions are only allowed if the total spin of the reactants is identical with that of the products. So in chemical reaction, there is no change of the total spin in the individual steps. It needs time that the total spin can change. So the origin of CIDMP is the spin selective recombination of radicals pairs. You create intermediate radical pairs and they may react back or further on, and inter-system crossing in this radical pair system is needed to change the spin that reaction to the singlet, usually the singlet ground state or some intermediate triplet state is possible. So this spin evolution involves electron and nuclear spins interacting with hyperfine coupling. So after these radical pairs end their reactions, after they go back to ground state molecules, the reaction products are enriched in certain nuclear spin configurations. You have some molecules with nuclear spins pointing parallel to the field and antiparallel. And one of these two possibilities is enriched and the other depleted. That's why we get, in the end, more reaction products with spins in one direction than in the other, meaning we have spin polarization. So, historical remarks. First, CIDMP was detected by Joachim Bargon and Hans Fischer in 1967. So the technique is older than 50 years. And first a wrong explanation was given, and then the proper one was given 2 years later by Gerd Kloss, Robert Kaptein, and Osterhoff. And after a couple of years, in 1982, time-resolved CIDMP experiments were carried out. I will come to that later because it's a very important step. And first applications to proteins were done by Robert Kaptein. Here, for example, we see the CIDMP spectrum below the NMR spectrum of bovine lactalbumin. And you see that here CIDMP is not only used to enhance signal amplitudes, getting better signal to noise, but also to remove or partly remove spectral crowding, meaning you can see individual lines which are not resolved in the NMR spectrum seen on the top. That was one of the main applications in the early years. So, CIDMP explanation, we carry on. We see here a reaction scheme. We start at ground state P. We shine in light, symbolized by H nu. We get to an excited singlet state, short-lived, and it goes by intersystem crossing to a lower-lying triplet state. And in the longer-lived triplet states, reaction, for example, is between the molecule breaks off into radicals, for example, and the radicals, that's important, start with the same multiplicity in the pair as the triplet, their triplet precursor. So we call this radical pair a triplet correlated radical pair. It still has the spins of the two individual radicals know about each other, and they start with an orientation that's the same as in the triplet of the precursor P. So in order to get back, for example, in this reaction to the initial ground state or to another diamagnetic reaction product P prime, we have to have a pathway that changes the triplet radical pairs to singlet correlated radical pairs with different spin orientation. And this is done by intersystem crossing, which is permitted because of hyperfine interaction in the nuclei, in one or in both radicals R1 and R2. And the spin evolution due to this hyperfine coupling changes the spin correlation to the singlet state. And from the singlet state, they can go down to the final reaction state. And since the interconversion rate depends on the nuclear spins, it is faster for one spin configuration as compared to the opposite spin orientation, meaning that some radicals with the proper spin configuration react faster back to the ground state, whereas those with the wrong spin configuration react slower. They can go from the triplet state to the singlet state only at a slower pace and come later. So what we see, here's another alternative description of this case. For example, we start with a di molecule and a quencher molecule. We excite the di molecule to its excited singlet state. The excited singlet state decays to an excited triplet state. From the excited triplet state, we have an electron or proton transfer between the di and the quencher. We form two radicals in that, but they are in their triplet state. They go by intersystem crossing to the singlet state. And this intersystem crossing is different for different nuclear spin configurations. And then you have a terminating step going back to the ground state molecules. So we sum up. Chemically induced dynamic nuclear polarization is based on the spin selective intersystem crossing in the short-lived intermediate molecules. It relies on the principle of spin conservation. As I said, all chemical reactions are spin selective and allowed only if the total spin of the reactants is the same as that of the products. So the nuclear spins affect the reactivity of the whole process. And some reaction products are enriched and others are depleted. And this gives rise to anomalous amplitudes on phases of the NMR spectrum. We see some NMR lines enhanced, stronger or less strong, or we can also have negative NMR lines. And this, as we will see, is a frozen signature of the short-lived reaction intermediates. From the NMR spectrum, we can trace back the properties of the intermediate species, which are maybe optically silent because they don't have a radiative channel, or we, as the other way possibility, we might see their spectrum in EPR, but EPR may be too insensitive because the intermediate radicals are just too short-lived. And then they are what we call elusive in the ESR spectrum. And CIDMP can be used to analyze these intermediates, how they are formed, what their properties are, and how they react further. And we will see some examples for such an analysis. So the optical nuclear polarization, the light-induced polarization is not only for enhancing intensity in NMR spectra, making them more sensitive for detection, but it also allows the analysis of processes going on in such radical pair reactions. So often you see for CIDMP explanation a so-called vector model. And you see two cases, up and down with blue and with red arrows, two radicals. And the vectors represent the spin state of the two electronic spins in the two radical partners in a radical pair or in a biradical. And the electronic spins experienced because of certain differences in their G factor or because of hyperfine interaction when spins are pointing, nuclear spins are pointing upwards or downwards and add their local fields to the external fields. That's how we can show a different speed of precession around the B-axis pointing upwards here in these individual plots. So spins in the alpha direction, shown in red, experience a lower local field as the beta spins, because in one case, the Zeeman field adds to the hyperfine field, or you see the difference. And you see the precession frequency is between the initial triplet T0 state that goes because the two radicals are dephasing. It goes in this precession to the singlet state S. And you see for the blue case, between the left and the right presentation, the blue arrow has turned by 180 degrees, and it's now oppositely showing to the black spin projection of the radical 2 of the pair, and it is in the singlet state of this radical pair system, whereas the red arrow has precessed slower and has not yet reached the singlet state. The radical pair is only in a superposition of triplet and singlet state, but has not reached the singlet configuration. And this means that for all molecules with the beta nuclear spin polarization, the intersystem crossing rate is bigger, is faster than for those molecules in the alpha nuclear spin state. So the blue spins are reacting faster, and in the product of the reaction, you see more nuclear spins in the beta state than in the alpha state. And that leads in the recombination products to more spins pointing down, giving a negative NMR line, and the positive NMR is smaller than the negative, and you see an enhanced negative NMR line in your spectrum. Here, it is shown once again. You have the di molecule radical and the quencher radical shown here. You have different G factors. The G factor of the di radical is here, is on the left, whereas the quencher is further on the right. The difference is delta G times mu times B0 for the energy difference. And because of hyperfine fields of the nuclei, we have in the quencher molecule, which is supposed to have one nucleus, another term adding or subtracting from the Zeeman field getting from G times mu times B0. And the center of the spectrum is split to alpha and beta spectral component. And from the size of the blue versus the red arrow, you see that the blue one, molecules with a negative, move faster, precess faster than the red ones, and you gain more molecules of the negative spin orientation in the reaction products. You see negative lines. This process is called spin sorting because all of your molecules in your liquid system, there are those with alpha and beta spin orientation, and you sort them first. In your NMR spectrum, you see the molecules with your beta spins, and only on a slower pace, those show up with the alpha spins. So in the reaction rate, you see, we come to that later, we see the molecules first with the alpha spins. So the CIDMP level which you observe depends on the radical pair lifetime. If the radicals decay before, let's say, the slow spins have crossed, then we don't see them in the NMR line. The spin dynamics that lead to the change of triplet to singlet character, the intersystem crossing, needs time to develop. So the reaction can start when here, for example, shown when radical R1 and radical R2 meet each other. They move along in the liquid, and once in a while, they meet each other. And only then they can see what the state of their spin correlation is. And each time they meet each other, this spin correlation is measured as the probability of intersystem crossing. So what we need is once in a while that the reaction partners meet each other. And they start from the center, represented by the gray ball, where they are formed. And then you see the trajectories of the two molecules which move in the soup, and once in a while they meet again. This is fairly often the case in the very beginning, when they are still in what's called the solvent cage. That's another word for the probability that they don't escape from each other. So by diffusion, they move, and once they are beyond a certain limit, the probability that they meet each other is so small that they can be seen as individual radicals without spin correlation. They move in the solvent as what's called free radical pairs, F pairs. And here in the very bottom, you see some formula describing the time for the first collision between the radical pairs by diffusive motion of the two spins. I don't want to go into more detail here, but what's important that after we start with a spin correlated pair, which is symbolized by the upper bar here, by diffusion in the soup, we get those radicals which did not recombined in the primary solvent cage. And these radicals move in the soup and can again meet each other, and we get what we say bulk, what we call bulk termination processes. Termination between individual pairs of radicals which have lost their spin correlation. And they can come now when they meet each other, then they form with their instantaneous spin state either a singlet together or a triplet state. A triplet state either in the T0 or in the T plus minus substates. And the reaction rates, the reaction probabilities when they meet in such an encounter are different once they are in singlet, in triplet 0, or in triplet T plus minus state. In the singlet state, they can form the final reaction product. And because they are depleted in beta states, these two nuclear in the nuclear beta state, because the alpha state is left, the beta state has already in the geminate process decayed. They are enriched in the alpha state. So the reaction products, now you see at a later moment molecules, product molecules in the alpha state, meaning the overall nuclear spin polarization decreases because of such termination processes. Once they are, however, in meeting each other in the T0 state, they act as the exactly as the initial radical pair, because it's in the same state as after the formation of the radical pair. So we gain again beta polarization, whereas in the T plus state of encountering, they have no recombination and may have to wait for another encounter. So we have three different back reactions once they are in the S state, in the T0 state, or in the T plus state. So everything is superimposed. And in addition, we have the thermalization of nuclear spins in the radicals. And we have involved nuclear spin polarization in the radicals with a characteristic reaction time T1 sub T sub n 1 that leads to a loss of nuclear polarization, which we created in the process. And that's because it's going on in the radicals, is occurring usually on the microsecond time scale. So this is shown here in a recent publication by Olga Morozova and Konstantin Ivanov from the ITC in Novosibirsk. Here it's shown in a pictorial way. You fill in your two quencher and dye molecules, you shine in light. This is excited, creates a triplet excited state. Then they react, form electron transfer. You have a dye and a quencher radical. Then you have your spin sorting process, which I try to describe. And then you have in-cage polarization, meaning geminate polarization, those molecules which react before they diffuse apart, and they give beta polarization. And those which are escape the geminate cage, they have alpha polarization. And they can, of course, then in the F pairs can create this, have these three processes which I described before. So when you see the time evolution, how CIDMP is being formed, you have the geminate reactions where you see molecules with, here is only the magnitude of the polarization shown. So you see the rise of your beta polarization because the termination reaction in the primary solvent cage, which is called geminate reaction, because the two reactants are twins, Gemini. So it's geminate reaction, and it occurs on the nanosecond time scale. And the other processes in the F pairs, the free pairs that radical pairs that meet in the bulk. And you see here first only those which meet in the singlet as zero state, and they have a termination reaction of opposite sign of the wrong enrichment. Or here, that is in the violet curve. if you add the nuclear spin relaxation in the radicals, this the alpha spins, which are left in the bulk radicals, is partly changed to the beta orientation. So the termination is not as efficient as you might use. New alpha, new beta spins are formed, and the CIDMP does not decay to zero because alpha and beta radicals are fully compensating each other. And in the red curve, you see a contribution coming from encounters when the two molecules are in the T0 state and form similar polarization, same polarization as in the geminate case. And the overall time evolution of CIDMP is given by the red curve. Different steps, and from the analysis of the shape of the time evolution, you can analyze what, for example, nuclear spin relaxation in the radical stage is. You can see how the branching is, and so on and so on. So you see in the CIDMP time evolution traces geminate CIDMP on the nanosecond time scale, whereas you see on the microsecond time scale the recombination of F pairs in termination reactions and in new CIDMP formation because of encounters in the T0 state. So this analysis I will describe in the following
Hans-Martin, I'm sorry, we still have time before the next session, but you're speaking for a bit more than 1 hour. Please keep that in mind.
Yeah, I still have 20 minutes, yeah?
Well, in principle, yeah, next session starts in 20 minutes.
Oh, yeah. Okay.
But I guess it's better to finish a bit earlier so that there is time for questions.
So, here you see a scheme of this time-resolved CIDMP. How you do it? You have a pre-saturation killing by irradiation of radio frequency, all polarization. Then you shine in light. You create your reaction partners by light. Then you have a variable delay where you have your spin evolution going on. And then you have your detection by a standard NMR experiments with an RF pulse, pi/2 or shorter pulse. You see the free induction decay, you do the Fourier transform, and you get the CIDMP signal on the bottom. Here, from the geminate CIDMP spectrum, meaning after at observation, after a few nanoseconds after your laser pulse, you can see the size of the coupling between the spins. So if you have more than one nuclear spin evolved, you can analyze, and from the size of your CIDMP effect, you can measure directly the size of your hyperfine coupling between electron spins and nuclear spins. A direct correlation, a linear correlation between the size of the CIDMP effect, meaning the CIDMP intensity, and the hyperfine coupling constant. This is a very powerful tool for analyzing your intermediate radicals. This is shown on the right-hand side for the case of benzophenone as a di and tyrosine as sequential molecules. What you get is a hyperfine coupling in the benzophenone and in the tyrosine molecules. And this can be analyzed in a theoretical way using what's called the Adrian model of radical pair CIDMP. And you see that for this linear correlation is almost exact for molecules with a higher number of spins, of nuclear spins, whereas for one or two nuclear spins, it doesn't work so nicely. So with time-resolved CIDMP, this is summarized here. You can separate with time-resolved. You can separate geminate and bulk reaction processes. You can get analysis of the hyperfine interaction. And for this, it is very important that you really measure your CIDMP in a time-resolved way and stop at the end of geminate evolution. Otherwise, because of these secondary processes in the bulk, this correlation is fully lost. And there are many cases in literature where this was not observed, and thus the analysis was totally wrong. So from the full time dependence over a couple of microseconds, you can analyze the processes that are involved in the reaction kinetics. You can get information about the exchange of electrons, electron transfer, proton transfer in some molecular reactions, or proton-coupled electron transfer in short-lived radical reactions, or you can analyze relaxation processes. And this can, of course, be affected by external parameters as the pH of the reaction system, or addition of gas molecules, which may use as parallel quenches, for example. So here, some examples in photolysis, light-induced photolysis of molecules. The molecule M, which is excited, breaks off in two radicals, and they react in the geminate reaction and in the bulk. And you can analyze, for example, the reaction timing. Or here you have quenching reaction where you excite a dimolecule, it encounters a quenching molecule, electron, for example, is transferred, you create two radicals, they move back in geminate reaction, or they diffuse in the bulk, and the reaction is ended there. So here are typical reaction partners, for example, amino acids, tryptophan, tyrosine, histidine, and so on, or dyes on the right-hand side, typical molecules which are used is benzophenone in different ways, dipyridine, DP, and so on. I don't want to go into details here. So, for example, you can use a radical pair reaction, and you can add a third molecule as an external additive, and depending on the concentration of this additional quencher molecule, the fate of the guanosine monophosphate is changing, and from the variation of the bulk process, the bulk CIDMP amplitude as a function of the concentration of the additive, you can measure the reaction rate here. Is it called K sub R between the phosphate and the cysteine. Here, to show you some experimental details, is the irradiation scheme. What is you want? You have to shine in light into your sample, and that's either done by a prism and from the side by, in the subplot A, from the side by a light guide, or it can be done by light guide from the top and then if the light guide from the top is realized by or is coupled by a flexible light guide to the laser, you can also move the NMR probe up and down, and this is important later by field variable experiments using CIDMP. So here is another situation where you want to measure the rate or the motion of residues in protein. You have here some side group tyrosine in ubiquinone, and you want to see how the tyrosine and what time scale the tyrosine is moving and the backbone. How you do it? You measure the relaxation rate, the nuclear relaxation rate in the radical stage when you have excited the tyrosine by encounter with the excited dye molecule, and you get a radical pair between this tyrosine radical and the dye molecule, and what you can measure is T sub 1n, the nuclear relaxation rate in the intermediate radical pair in the tyrosine, and as I said, this changes the evolution of the bulk CIDMP, and from this time variation then you can get this relaxation rate, and from this relaxation, when you compare it to the same reaction and the free amino acid, you can analyze by the so-called model-free analysis introduced by Lipari and Szabo how the side group tyrosine moves around the backbone of the protein chain, and you get the time of the diffusional diffusion around a cone about the fixing point at the protein of this tyrosine. You get what's called an order parameter. If you did it, you know what I'm talking about. Otherwise, it is the opening of the cone of this restricted diffusional motion and the timing. This is what you get out in complex system. So you get reaction time and relaxation from the time. Now,
Hans-Martin, I'm sorry. It's
10
the
minutes.
time is really running fast.
Yeah, I'll try to change. So we go to variable field. You see now when you observe your chemically induced dynamic polarization at variable magnetic field, it changes. It changes with field rapidly. Here it's shown for the field range to 7 Tesla. And you can see it even more pronounced when you go to a logarithmic scale of the field. You see at low field, strong polarization, and at high field, whereas in intermediate field range, the observed polarization is rather small. So from the polarization, from the analysis of the field range, you can get information on radical structures, for example. What you can refer to, and this is what I showed, the level crossing at high field is given by the difference in G factors of different radicals that are formed. Once the G factor is higher, the maximum of the field dependence is at lower field. And you can distinguish between here, for example, 3 different radicals that are formed in the quenching reaction between a carboxybenzophenone and this methylcysteine. And when you have it's in a cis form, the methylcysteine, you get 3 1-center 3-electron bond, which has a particular G factor, and you can distinguish it in the transform, where you have 1-center 3-electron bond between an oxygen and in the middle a sulfur and an oxygen, and on the left in the trans you have 1-center 1-electron radical, and all 3 radicals have different G factors, and that's why they have different maximum in their CIDMP field dependence. So this is shown here, and I have to go through this series of slides fast. Here you observe these 3 different G factors of the radical with different electron concentration at the carbon. So now that was all at high field. At intermediate field,
Hans-Martin, it's already time to start with posters.
Yeah.
So could you perhaps
I'll
summarize it?
I'll stop.
And I guess that we also have a question in the chat, and perhaps there are some more questions.
Okay.
Let's leave just a bit of time for discussion and for having a technical break.
Let me just mention that in the intermediate field, you also have other features which are important for analyzing the electronic spin-spin coupling in radicals, radical pairs or biradicals. And you have a feature in the field dependence, as I said, at low field. So you can get from the field dependence altogether the G factors, the electron exchange interaction, and the hyperfine coupling of your short-lived radical pairs. And this is a very important tool for analysis of these short-lived radical intermediates. I go through the individual parts where this is shown rather quickly, and if you have questions, of course, I'm willing to answer this. What I didn't have enough time for is talk about some experimental details. Also, this I can give more information in the discussion. With this, I would like to end my talk. You see that light-induced hyperpolarization is not only good for increasing your signal amplitudes in NMR, but gives you many tools for analyzing light-induced processes in liquid and in solid matrices. And with this, I end my talk, and I thank you for listening.
Okay, thank you very much for this very detailed and enlightening presentation. I see that there is one question in the chat again from Georges Menseljan. So question is, so with CADNP you can access the isotropic value of the hyperfine coupling. Could one transfer this experiment with the same chemical system in solid state and obtain the full hyperfine tensor components?
In the solid state, as this ONP, which I started in the beginning, you can get several elements of your hyperfine tensor. And of course, in principle, if you measure the full orientation dependence in your crystalline system, you can gain at least the principal values of your hyperfine coupling. You can get the principal values, of course, of your zero field splitting tensor, and so on. So it takes many experiments because you have to get the full ONP depends along the principal orientations of the involved tensors.
Okay, I hope, well, yeah, this answers to the question, I guess. I suggest that we start poster session 15 minutes later, so we have now a few more minutes for questions, and we start, well, 15 minutes later, basically in 12 minutes or so. So just that all participants have a bit of time to relax. The question is from Jianzhan Zhao. If we use triplet state to induce CADNP, how long the triplet state lifetime should be? Thank you for the nice talk.
So that depends really on how you start in your reaction. There are so many different reactions, but of course, what's important that the triplet state lives long enough that the triplet, that an electron transfer process is possible. That's for the starting triplet. There are also reactions where you start your reactions with a singlet. And because of spin evolution, only this intersystem crossing in the radical pair state leads to a triplet. And this triplet, in some cases, can be also analyzed. I didn't go into all these different situations. So there are so many various forms and subcases that I cannot answer this without getting another hour of my presentation. So the initial excited state can be a singlet, and from that state you create your radical pair, and in the radical pair part of the system evolves into a triplet state. Or you start with a triplet state and it goes back via all the processes which I discussed into the singlet starting state. That's for cyclic photoreactions the main case, and this I discussed in more detail. But there are so many other cases that can be discussed individually that I cannot fully answer your question, how long they have to live. They have to, usually the triplet state has to live long enough that the radical pair is formed. And then in this radical pair, the triplet evolution is on the microsecond scale, because in the bulk processes, the individual radicals can encounter in a triplet state, which is then evolving, or they encounter in a singlet state. So the triplet state is newly formed in F-pair encounters.
Okay, I guess this answers to the question. Well, I don't see any further questions. So then let's, I think Hans Martin again, so I also clap my hands.